Thank you for showing up. Aaron and I were joking. We've got obviously competing sessions going on here. My goal today really is a few things to get at. I want to review historical changes in climate that have happened in the Midwest. I want to present what the global circulation or global climate models are suggesting is going to happen over the next 50 to 100 years in terms of weather and climate. Describe some of the impacts and challenges that we've already seen and that we're likely to continue seeing in terms of ag. And then, the whole idea here is thinking about how are we going to build resiliency in our agroecosystems, as well as managing our natural resources, so our soils, water quality, and so forth. So, so I just wanted to start with, a lot of times when I talk about this, start with the grand challenges for what we're facing. And these statements really have come out of a couple of reports that were put forth by the Association of Public Land-Grant Universities in 2010, and then a follow-up report by the Crop Science Society of America. The whole idea here is that we've got to adapt and mitigate the impacts of climate change on food, fiber, and fuel systems here in the U.S. as well as the world, obviously. Increase the speed with which we can adapt, given the pace at which changes in climate are happening. By using crop science to address abiotic stresses such as heat and drought. Those are the things that we hear a lot about and how that impacts productivity. And to create future novel cropping systems that are resilient in the face of changes in climate and rural demographics. And I just add at the bottom, really trying to protect soils and water quality. Much of the focus, if I am talking in class or speaking to certain groups, they think of resiliency. They're thinking about how do we maintain productivity or increase that moving in the future. And that's really just one aspect when we think about building resiliency. I guess my goal when I speak about this is to think of it much larger in terms of other ecosystem services that the landscape provides to humanity. It's not just about how much food or fuel or fiber we're producing. It's also protecting, I must have skipped ahead here, other ecosystem services such as the surface water quality, groundwater quality, how much biofuel we're producing, how are we able to regulate floods. We've seen this time and time again throughout the Midwest just in the last 10 years. The problem is that there's no ideal scenario that maximizes all of these ecosystem services. There's trade-offs. And what policy decision makers really want is basically one number and one answer that they can move forward on, and it's not really that simple. In some cases, a scenario may maximize groundwater quality, but it may minimize the amount of food we're able to produce. That's just one example. So I'm going to come back to this at the end, but I just want you to keep that in mind that what choices are going to increase resiliency, not just in terms of productivity, but other natural resources that we depend on. So, the first thing to think about is, how does weather and climate ultimately impact agriculture? And I could spend a whole day talking about this particular topic, but this is really the biophysical perspective. This is where I live in terms of my teaching and research at the university. So as you probably already know, when we talk about weather, you hear me say weather, that's the short-term, high-frequency variability. That's the hour-to-hour, day-to-day, month-to-month type of changes that challenge growers throughout the world. The climate is the long-term trend or the long-term average, as you might think of. And that's usually based on a 30-year averaging of daily climate daily weather information that's collected. So our most recent climate averages are based on 1981 to 2010. When 2021 comes along, they'll update those again up to the 2010s. So I've already mentioned the productivity aspect of it. It drives what types of crop types we're going to plant. Are you thinking, what crop type, C3, C4, perennial, annual? What variety are you going to select depending on how many growing degree days you might have, what the length of the growing season is. It impacts livestock functioning and management, how we manage our water, the fertilizers that are going on, our tillage activities, planting and harvest dates, or replanting in some cases, the equipment that's used, the pests, the disease outbreaks, those types of things that we're dealing with, the weed and crop interactions. Weather and climate impacts, obviously cycling of organic matter, how much nitrogen might be leached through a system and make it to the groundwater. And the other point really about the Midwest is that we're very diverse in terms of what we do here. Wisconsin in particular, the upper Midwest states, and the ramifications of a changing climate is pretty big across that geographic scope. So I'm just first going to highlight sort of the recent reports that have shown how climate has changed across, the focus here is on the US. So what this chart is showing is an observed annual US temperature change comparing a 20-year period up through 2012 compared to the first 60 years of the 20th century. As you can see, there's a lot of red on that map. So that's just showing an increase in annual average temperatures somewhere around 1 to 2 degrees, depending on Fahrenheit where you are. If you focus on the Midwest US, there's a lot of some of the deepest reds there, with some of the most pronounced warming happening in our northernmost locations. I just threw this in here. I know this conference is focused on the Midwest, but I have some very more detailed information on Wisconsin that we published several years ago. The reason I bring this up and present these trends is that it's not a one-size-fits-all. So there's definite differences depending on what season you're looking at, as well as whether you're talking about daytime highs or nighttime lows. So what we've done here is broken up the 4 seasons. Shades of green and yellow denote places that are getting warmer from 1950 through 2010. Shades of light blue and darker blues are places that have actually been trending a bit cooler, although sometimes it's not statistically significant. So the main takeaways here is that there's a lot of variability, but the greatest amount of warming has generally occurred in winter and springtime, as well as with the nighttime lows. So nighttime lows are generally warming at a pace that's about twice as fast as daytime highs. In fact, in many places across the Midwest, daytime highs during the summer have not really increased at all over the last 50 to 60 years. It's really those really nighttime lows, particularly in wintertime, that's hard to convince given what we're going to go through in the next week or so. But that's really where most of the change is occurring. And I just want to mention, if you see any, yeah, go ahead.
So just for me to get a framework, so the nighttime low is going up, is that a pretty strong function of increased humidity?
Partly, yes. So there is also that change that's been happening. Dew point temperatures have been trending upward, which is basically a response to increased humidity. So yes, at night then the air, it doesn't lose its heat as readily. So that's definitely part of it. And the reason for sort of this discrepancy and sort of a non-change in really hot days to this point is also related to this too. And also probably related to the increased planting density of a lot of row crops and the amount of evapotranspiration that's been going on. Some of those things are not characterized well by climate models. Yeah. So I was just going to mention that if you see any references or anything up here with names, I'd be happy to upload those to a site where at some point you can download those for your own reference. This is a lot of data that's being thrown at you in an hour, basically. So I put this together just given kind of what you're thinking about the weather right now and what's probably going to happen next Wednesday night when it's forecast to be minus 22 Fahrenheit here in Madison. If you look at how many record highs versus lows are being set, there's a much higher frequency of record highs being set than record lows. And this is just for the Madison airport showing, and I just updated this through yesterday, 84 record highs from the year 2000 through yesterday, and only 18 record lows. And there's actually 1 month, January, that hasn't set any record lows. And I look back, the last time we set a record low in January in Madison was 1994, when we had 3 straight days of minus 27. If you're thinking next Wednesday night, when everyone's talking about this polar air mass coming here, the record low next Wednesday night in Madison is minus 37 degrees, set in 1951. And that's the all-time minimum temperature ever recorded at the Madison airport. So minus 22 might sound cold, it's still not even approaching where we're at. Most of our record lows right now at this time of the year are really minus 25 to minus 30. But the main point is that this is sort of what we're seeing. And there's lots of record highs being set in many of the months. Obviously, some of the colder months are where we're seeing the most records being set. So a lot of this warmth in the shoulder seasons, as I call it, has been extending the growing season. So on average, if you look at the graph in the left there, that shows a +9. So over this comparison of the earliest part of the 20th century versus that 20-year period, about an extension of maybe 7 to 10 days. The more detailed analysis that I've done for Wisconsin shows that there's some places that have had an increase in the growing season of maybe upwards of 3 weeks since 1950. And you can imagine what that is doing to phenology, crop calendars, planting dates, which I'll touch on in a minute. It's a very significant change in a very short period of time.
Does that correlate to degree days too, an increase?
Yes, yeah. And I didn't put any of those in here, but yeah, you can think of sort of adding, an extra week or two on the cooler season. Well, that might add maybe 50 to 100 growing degree days, base 10, but it still might be enough where you select a different hybrid, depending on where you're at. Yeah. Trends in precipitation. So a lot of green on this map is showing it's getting wetter in a lot of places. There are some places that are getting drier, but if you look at the concentration of greens and shades of green in the Midwest, it's definitely been trending about 10 to 15% wetter, over the last century. What does that equate to? About an additional 2 to 4 inches of rainfall each year. 4 inches of rainfall additional each year is equivalent to 1 more summer month of rainfall. We average about 4 inches per summer month in the Midwest. So it's a pretty significant change, again, in a short period of time. Just here in the Madison area, you can sort of see this overall trend over the last 80 years or so. The bottom graph is the one that we're also more concerned probably about, is the increase in the frequency of very heavy rainfall events. So these are the 2 and 3 inch, 50 millimeter, 75 millimeter events in a 24-hour period. You'll see that, up through about, the 1980s, things were pretty consistent, and something has happened just in the last 2 to 3 decades. We've tripled to quadruple, the number of those types of events, and everyone's seeing that showing up on the news, or maybe in your own backyard, or in your sump pit, in your basement, or in your flooded fields simultaneously. Some of the other interesting statistics just from Madison, and you can pick any one of the observation stations in the Midwest and you'll get a similar result. These are the top 6 wettest years on record in terms of annual precip. 3 of the top 6 years have happened in Madison just since 2013. 2018 was only the second time we received 50 inches of rainfall over the year. Our average is about 35 inches. You might jump to a conclusion, say, well, obviously something really is changing, but I do point out that the other 3 years all happened in the early 1880s. You might remember that being a very wet decade there. But there's some parallel going on. You'll hear a lot of times about natural variability and cycles going on, and I think that there is some of that going on, but at the same time, there's also superimposed this greater trend in a changing climate. So, that's just something to keep in mind when you see records, but obviously these last few years have been, unfortunately, really, really wet. If you dig a little deeper and look at a ranking of when the top 24-hour precip events have happened here locally, 6 of the top 12 events have happened just in the last 19 years. That's over 140 years of records being kept at our airport here. You also might notice that the maximum 24-hour rainfall for this particular point on the map is only about 5 inches. This area, this county, experienced a catastrophic flooding event last August. Just 20 miles west of here, they got somewhere between 11 to 15 inches of rain, and that wasn't in 24 hours. That was basically in about a 6 to 8 hour period. That set an all-time state record. So oftentimes people might say, well, 5 inches, that doesn't sound like so much. It's just luck of the draw that this observation station didn't get the 11, 12, 13, 14, or 15 inches. It doesn't mean that it's not possible, it just means that it's just random chance where that thunderstorm may have developed and sat, for a few hours. So, yeah.
Is there any reason to think that that inconsistency has even gotten worse? I think there now with these weather stations that even in given areas, it's getting worse. In other words, it rains 3 inches one place and 10 over here and a half inch over here.
Yeah, it's a good point. We've got really good coverage, co-op stations, volunteers. It's not that expensive to put a weather station in your backyard. The variability during summertime can be pretty intense, and that's another thing. It's getting more chaotic. It's more unpredictable, and it's very hard to predict those events because they happen at such a small scale. And that small scale is really hard for the models that tell us what our weather is going to be in the next 7 days to resolve. And so I agree, it's definitely happening. It makes it really hard to predict and plan for. So the projections moving forward, and I've got a variety of graphs that summarize this. The upper left is just showing the degree of warming for the middle part of the 21st century compared to the last 30 years of the 20th century. It's looking at about, maybe 4 to 5 degrees of annual increase in temperatures over the Midwest. Days above 95, the frequency may be going up by about 5 to 15 days, or more, depending on where you actually are located. That's the upper right graph. The frost-free season, number of days, extension might be, we might see another 2 to 3 weeks of an extension of the growing season in the next 3 to 4 decades. And then obviously an associated increase in cooling degree days, which maybe we're not so concerned about in this talk. And I apologize, the transfer of the graph from a Mac to the PC here didn't work so well, but you sort of get the point. This is showing different scenarios from our climate models of how the maximum temperature change will likely look in the Midwest. And depending on whether you think of a low emission scenario of greenhouse gases or a bit higher, sort of business as usual, might see anywhere from a 3 to 6 degree increase in our summer maximum temperatures by the end of the century. Associated with that is an increase in the number of days above 90 degrees Fahrenheit. And the best way that I can summarize this to you is that in 2012, around here, Madison experienced 39 days above 90. The average is about 9. That's pretty typical for this latitude in this area. By the middle to later part of the 21st century, 2012 will be the average of what people will experience. We'd in this area be experiencing 30 to 40 days above 90. So if you remember 2012 and you like that, although maybe we'll get more rainfall than we did, that's sort of the temperature regime we're looking at moving forward. I don't think that makes anyone happy. And on the flip side, what we've really seen is a trend towards a decrease in the very cold nights, and that's going to continue moving forward. Just more very hot days and less very cold days. So this is another representation of the change in the growing season length, again ending up somewhere between 30 to 40 days, potentially longer by the end of the century, so almost an extra month. So if you think about when might you be planting your summer crops, does that mean mid-March, harvesting in maybe early October or maybe a bit later? On the precipitation side of things, the increase in precip is Modest, you might say, well, 1 to 2 inches increase on top of what we've already seen. That's probably something we can probably handle. I'll talk a little bit more in a minute about the increase in the number of days for heavy precip and sort of the wettest 5-day totals. Both go up, but the numbers aren't really all that startling when you look at it from this perspective. The models generally have a harder time agreeing on where precipitation is going to go moving into the future. The best guess is that it's probably going to get slightly wetter and most likely to happen in winter and springtime and not necessarily during the core of the growing season. So, and this is the problem. I know the thick line makes it hard to resolve, but that's the variability, and what the models are saying is the annual precip. So it's kind of slowly going up, but there's a lot of year-to-year variability. And that presents a challenge when we think about management of our ag systems and protection of soil and water. That chaotic nature, as we're talking about here, is a real significant challenge. This is the projections for the annual frequency of like 1 inch or more rainfall events per year. So think of it this way, maybe an extra 2 to 3 days each year would have 1 inch or more of precip falling. And then if you extend that and look at the change in 2 inches or plus in 24 hours, basically it adds up to about maybe 2 to 5 more days per decade. So, these are things we just normally would only experience maybe once or twice in a whole decade. And, it's kind of like we're continuing to increase that frequency considerably moving forward. And that's all over the Midwest, as well as all over probably the eastern half of the U.S. So I wanted to just touch upon that record event that I had mentioned. And that these are the things that I said were just very hard to resolve when we think about our models predicting the future. That particular event, if it was shifted 20 miles to the east, would have been catastrophic flooding in Madison. And we were already dealing with flooding just because of a small part of the watershed that we're a part of got part of that heavy rainfall. But this really got the attention of many people in the region saying, hey, how much more are we going to get? How often is this likely to happen? And we can't be thinking anymore in terms of, well, that was a 500-year event. You got to throw those things out the window. They basically don't relate to where we're at in terms of variability anymore. So I just wanted to spend a little bit of time thinking about how climate change and agricultural land management has impacted productivity and water quality up to this point. You might ask, well, are there observations, records of a changing climate and what it's meant to productivity? And you don't have to look into the literature very far. I could spend entire days talking about all the studies that have been done, but these are just some of the snips of the titles of some of the most recent articles. A lot of these have to do with impacts of drought, of extreme heat. A lot of the focus is on maize because of it covering 90 million acres in the U.S., and other things related to the trends of our yields and how they're insufficient to meet food demands by 2050. And partly because of the impact of a changing climate on productivity and how are we going to adapt to those changes. Some of the earlier work I did about a decade ago was looking at how a 30-year trend in temperature and precip across Wisconsin was impacting the trends in corn and soybean yields. The easiest way to explain this is what I've done is on the x-axis there for temperature. So I took each county. Each county has a 30-year trend in its summer temperature. It also has a trend in how its corn yield had changed. So if you regress those two, you end up with a relationship that suggests places that were trending warmer generally had a less of a slope of the yield trend in those counties. And the relationship with precipitation is that places that are generally trending a bit wetter actually fared better in terms of increasing their yields over the 30 years. If you add these things up, what we found is that it basically says that for about every 1 degree of increase in temperature during the core of the growing season from June through through August, you lose about 15% of productivity. That's pretty startling. That doesn't mean that we can't combat that with adaptation. It means if you don't adapt or do something about that, there's a high likelihood that yields are going to be challenged moving forward. But you'll also hear industry and people who do breeding and genetics say, don't worry about that, we've got that covered. We're breeding for better drought tolerance, better tolerance to high temperatures and that. But I think that there's already observations that show that they aren't able to keep up with that. We see these effects and they continue to happen.
The real key to that too is it's easy to kind of, I'd say in relative ease, it's easier when you've got 90 million acres of corn that they're doing research on. The problem I think we see, and we see it, we're apple orchard people, is this climate change in vegetables and stuff like this. They're the fringe crops, but there are food crops, and they're not shift. That shift is having tremendous effect already on it. And corn's going to be an easier problem to solve than this real direct food chain to human beings.
Great point. Yes, I appreciate that perspective. You're right. It's very hard to find, to do this type of analysis on those types of systems.
Exactly.
Yeah, we don't have the, yes, we'd love to, but we can't because we don't have the information. We don't have it long term. And there's definitely not the amount of resources, as you're saying, going into studying those things. Yeah, thank you. Yeah. Another significant shift, and again, I apologize because a lot of, as we're saying, a lot of this information is focused on corn and beans because of the amount of data that we have, but at least they're sort of giving us insight into what is likely to happen. We published some work that was looking at sort of the change in planting date for corn. So this is showing an overall shift of about 4 to 5 days earlier per decade for the Corn Belt states. In a follow-up study, we found that shift to earlier planting does what? Well, allows for longer season hybrids to be planted with greater yield potential. That probably contributed 20 to 30% of the yield trend during that time. The real question is, can we keep planting earlier and earlier? It's often suggested that that's going to be an adaptation to a changing climate. The problem is we can't plant our crops in February, and there's a reason for that. The sun angle, radiation intensity is not very strong. I mean, it's getting stronger. I mean, snow melts a lot easier at the end of January than it does in mid-December, but it's just not possible. So at some point, that effect is going to wear itself out, and we're going to lose that. And that's sort of been built into the system to this point.
If you
Yeah.
plant earlier, you harvest earlier also?
No, yeah. So I had a graduate student who looked at that, and basically the main shift has been just planting earlier, really no change in when sort of R1, the reproductive phase, starts, and no real change, although maybe harvesting a bit later towards the end. So a little bit on the end, extension, but more on the beginning. So it's basically extending the vegetative stage of these crops.
And so does that increase risk? Because now you have a longer period of time that the plants are exposed to too much rain, too little rain, too this, that, wind.
Exactly, yes, it is a greater risk. It's a greater risk if people decide to plant and you have what we call a false spring, like we had in 2012. 2 weeks of 80 degrees in March. Apples were, it was devastating to cherry and apple growers, but some people decided to plant, some of the summer crops, and then what did we have? What was the likelihood of getting a freeze event? About 100%, because we still had 6 weeks to go, and it unfortunately happened. So, yeah. The other point that I wanted to make about some of the contributions, we're dealing with the water quality issues. This is sort of the big elephant in the room around here in this watershed for those of you that are not in the Madison area. But, we have a tremendous amount of nutrients leaving the landscape, phosphorus loading for manure. We've got nitrate leaching to groundwater, unfortunately. And I bring up our watershed here as an example. This isn't just happening here. This is everywhere across the Midwest and other global places. But The two graphs there are basically showing the annual phosphorus load measured at 2 points in streams and rivers in this watershed, making their way into Lake Mendota, which is to the north of where we're at right now. There's been, despite 40 years of better management practices, millions of dollars invested by the county and the watershed into better management to reduce that, we've seen no decrease in the amount of phosphorus loading to the lakes, unfortunately. We've also seen this increased frequency of extreme rainfall events since the 1950s. This is a big problem. We've had this long-term goal to reduce this number by 50%, and we're just not making very much progress on it, unfortunately. And so you end up with situations where we get these algal blooms that turn the water this sort of teal-blue color. And this was just 2 years ago. It happened again last summer. And frankly, I'm getting tired of going on the local news and talking about why are we seeing this and how are we going to clean the lakes up. It's just, there's not a simple fix. Yeah, go ahead.
I'm just curious, you said despite 4 years of better management practices, can you give any more information or conjectures as to what's going on there?
I'd say it's largely efforts with, buffer strips, collecting leaves. They're small little incremental changes, along the landscape. And what the literature is showing, not just here, but like in Europe and other places, is that those small scale effects, if you test them on an individual field, they seem to work pretty well. When you start to scale them up to a whole watershed, they don't seem to have the same effect. And it might be because there's a disproportionate amount of runoff coming from just a few places that aren't really handling the problem as well. So, and for those of you that are local here, there's a large effort to clean the lakes up, and but we just aren't getting anywhere, unfortunately. Yeah.
Unfortunately, part of the problem is, a lot of what you're talking about managed has been a voluntary process. And if you look as a side by side to what's happened in the Chesapeake Bay, which became a mandatory process, they've got tremendous results comparatively to what generally is accepted practices here in the rest of the United States. It's a phenomenal difference.
Right. Yeah. Yeah. You first. Yeah.
I think what they've also found here in Dane County is that there's legacy phosphorus that's in the stream bed.
Yep. Yeah.
They actually started to excavate some of it to try to reduce the amount of it.
Yep. Yeah. Go ahead.
So is the primary offender, is it ag-based?
Unfortunately, yes. Yeah. Yeah. Yep. Yep. And that application over decades to a century has built up that amount in soils to the point that we really wouldn't need any fertilizer for 100 years, given the concentrations of P that are in the soils. So, yeah, go ahead.
If you go back to your last slide with factors,
Yep.
is there any correlation to the high points and rain events?
Yes. Yep. Yep. 2008, you might remember Iowa, Cedar Rapids flooding. We had devastating flooding here in southern Wisconsin. We got like 15 inches of rain in the first 2 weeks of June. So, yeah. So there's definitely a weather variability signal there. Yeah. Does someone else have their hand up? Yeah, go ahead.
Well, with the Madison lakes, do you have a measurement for phosphorus in parts per million that is causing this
And
in the lake itself?
well, we know what the concentration is. We also know what the load is coming in. It's really more of the load that we're concerned with, the whole budget of the watershed. Yeah. Yeah. It's well studied. Yeah.
Well, is it greater than 1 part per million in the lake of phosphorus that is causing this?
I don't remember the exact concentrations, but the amount that's sort of making its way into the lake is a very small fraction of the total budget, which makes it really hard to control, unfortunately. Like, you don't need that much to cause the problems we're seeing with water quality. Yeah. So I think some of this we've already actually covered by your questions, but we've had this long-term goal. Despite all the planning, we haven't reached it. We've got legacy soil P, climate change, and we've invasive species, which I'm not going to talk about. Those are actually in the lake, not actually on the landscape. changes in our human demands. We're underestimating the time, the money, everything that's really going to take to make a change on the landscape and reach that goal. On the groundwater quality, some of you may have seen this article in the New York Times in November. It was talking about a town in central Wisconsin, Armenia, that was measuring 45 parts per million of nitrate in their groundwater, which is obviously 4.5 times above the 10 part per million EPA safe drinking water standard. This is not going away either, and this is also related to a legacy nitrogen problem in our soils. And there's been plenty of studies that have shown that even after you shut off that nitrogen going into the system, it may take decades for the system to actually recover and get below a safe level. So a lot of people think, oh, it sounds like doom and gloom and there's nothing we can do, and I don't really think that way. I think agriculture has been adapting for a long time to gradual changes in climate, and even though if I get in a room, and here's my historical sort of experience with growers and farmers, is that the surveys show a lot of them don't think that climate change is actually happening. Although we have data to show that they've actually been changing their management practices to go along with those changes and are benefiting in some ways from those changes. So there's been adaptations taking place, and that will continue. What are some of the key challenges we're thinking about? Well, if we just focus on productivity, you can think of any crop. I just use corn, obviously, because that's what we do a lot here. And you think of extending that current trend, but what happens is we get 1 degree of warming or 2 degrees of warming, or we take away the planting date effect. Eventually, the slope of that line is going to decrease. And we've already seen that with some of our crops across the U.S., in particular wheat in the central Great Plains. There's some places where corn and soybean trends are outpacing others, and the yield gap is sort of widening between the winners and the losers. So we already see this going on. Here in this watershed, just another example, the extreme precip, more soil erosion, more phosphorus washing and nutrients in the waterways. Unfortunately, what our research has shown, and you don't even need to understand the graph, is that there's a synergistic effect between high soil P and extreme rainfall, meaning that soils that have a higher amount of concentration of P are even more sensitive to heavy rainfall events, meaning they contribute even more than lower soil P that their counterparts would. This is a big problem. The amount of soil phosphorus in the Midwest is not going down. And when you remove soil phosphorus through the plant growth process, crops only remove a very small amount every year from the soil based on their nutritional needs. There's a huge pool of phosphorus sitting there and only a small amount being taken up each year.
Does any of the solubility of the phosphorus, is it tied at all to the pH of the rainwater?
I can't say that I know that for sure. I haven't heard anyone study that here. I'm glad you mentioned the solubility part of it, though, too, is that part of the reason a lot of the management effects have been failing or not doing what people would think they would do in terms of trapping phosphorus and keeping it on the landscape is that about 50% of it is in dissolved form. So they're only able really to account for half of the problem. And if anyone in this room can figure out how to stop water from moving on the landscape, you'd be a billionaire and everyone would want to know the secret on how to do that. But that's really part of the problem too, is the solubility aspect. Yeah?
Are you familiar with any of Jerry Hatfield's research, where he actually talks about the problem, a lot of these problems, it's not nitrate leaching, it's not phosphorus leaching, it's actually hydrological changes due to the way that we're using the landscape. So his example was if you change X amount of Iowa back to small grains or grasses, it changes the way the hydrology is affected through the spring, the amount of runoff, the amount of leaching. Just, yeah.
Yes, definitely. And I end up with Jerry at some conferences talking, but yeah, and I've got a slide that we'll get to that a little bit in terms of maybe a potential solution moving forward. But you're right, the land cover they'll change itself from going from perennial to annual is a huge impact on the hydrologic cycle, not just in terms of the water moving on the surface, but also how much evapotranspiration you have, how much is leaving the root zone. So I'm glad you brought that up also. Good point. And just another point here is that 3/4 of the amount of phosphorus that makes it into the lake here only happens on 29 days that it rains. Yes, we usually get about 100 days each year where there's some rainfall. So it's only on 29 of those days that 3/4 of the load makes it into the lake. So if we can figure out what to do, and how to adapt to those real heavy rainfall events, we'll be in a much better place, hopefully. So, and just the other big point, this was a study in Science that was published in 2017, just showing, they used a model that superimposed changes in precipitation and other changes in climate to run through how the total nitrogen flux through watersheds would be changing. Those are the near future, the B panel and the C panel, the far future, showing just the increase in the amount of nitrogen that's going to be moving through the system. So again, this is getting back to the changes in the hydrology. It's not necessarily that we're going to be adding more N to our systems. In fact, hopefully we're going to be adding less as we become more efficient in our use, but it's that change in hydrology and the runoff that's actually going to be taking place. It's going to move more of that available N through the system. So I've got a list of, I think, 10 areas or challenges that I see that, we're going to be faced with. And, nitrogen management, you think about how it's challenging now, think of a more chaotic precipitation pattern. Planting earlier in spring, as was brought up, exposes you to even more time when you may get heavy rainfall events. It's just going to get very much more challenging to control nitrogen on the landscape and keep it in the root zone and keep it from making its way into surface and groundwater. If you're talking about a system where irrigation is taking place, the water management is going to become more challenging, not just in terms of the chaotic nature of when rainfall happens and how much, but warmer climate will mean more evapotranspiration, probably a higher demand for water. So we're likely to see water use maybe go up. It's obvious that soil management will be challenged with more erosion. Maybe tillage operations might be more challenging, depending on what time of the year and, can you get out? Is it dry enough? Did we just have a gully washer? Those types of things. Pest and disease management, warmer temperatures during winter, more overwintering of certain pests. New pests and diseases showing up in areas that didn't have those, 10, 20, 30 years ago. Temperatures as they warm, maybe they'll start moving outside the optimal physiological range for those cropping systems. In this state, I think of potato in the Central Sands region. It's a cooler season crop. It's got a kind of a limited, window there. We move too far outside of that window, and it's going to be devastating to some of these crops that probably prefer the cooler temperatures. Those increase in growing degree days are going to increase the rate of phenological development. That'll potentially change the timing of certain key events during the season. We talked a little about an earlier onset of spring, higher frequency of false springs, increased soil moisture stress. Some people suggest that increased atmospheric CO2 is beneficial to C3 crops, let's say like soybean, but a lot of our weeds are also C3 in terms of their photosynthetic pathway, so they may actually flourish more as we move forward. And then we also talked about more challenges to planting and harvest seasons with more variable weather. So a lot of the weather changes are really crucial here. So what are some of the ideas to adapt and increase resiliency, coping with this, with a new climate system? So the first thing I'll say is that, the key challenges are that, future generations are going to confront, climate and weather that is unprecedented. There's no analog really out there to allow them to understand what's likely to be coming. And the projected magnitude of those changes is often hard to comprehend when you're not really able to experience that previously. And there's this idea that stationarity is dead, and what does that actually mean? It means the amount of daily, seasonal, and interannual variability historically that typically we've used for planning, whether it be like how big of a culvert, do you need to dig, or anything else, is not going to be very useful for future planning because we've moved sort of outside that range compared to the historical record.
I'd argue that,
Yep.
back that slide, that
Yep.
really is a significant thing for engineering, like in utilities, or
Mm-hmm.
not utilities, but in like roads and culverts and bridge designs.
Yeah, that's right. Yeah, and a lot of the current designs of what we're dealing with go back to like precipitation that happened in the 1950s, and that's why you're seeing what you see now. In terms of when we get a heavy rainfall event, why wasn't that able to withstand that? Well, that wasn't the way rainfall happened back when they made those decisions. So it's really getting outside the box thinking and maybe outside of a comfort zone in terms of planning. This quote that I found, I think, is really telling. I'll just read it. Until recently, we could reasonably rely on observed means and variability as the frame of reference for sustainable environmental management. However, the current pace of environmental change is moving us outside the envelope of historic variation. It's becoming increasingly apparent that we cannot rely on historical variation alone as the basis for future management, conservation, and sustainability. So that sounds like a lot of doom and gloom. It just means that we've got to pay a little bit more attention and trust the models moving forward, in our planning. So some of these ideas for increasing resiliency, are probably already on the radar of many of you in the room. Conservation tillage, cover crops, obvious choices. I work with some people in the Department of Agronomy that just want to perennialize the whole landscape. Get rid of those row crops, just plant perennials. Diversity in terms of hybrids and varieties, when possible. Maybe that's possible for some cropping systems. Maybe it's not for a perennial tree crop. Maybe there are some limitations. How to phase in new crops and rotations, the improvement in genetics, what plant traits should we really be selecting for and breeding, modification of planting and harvest dates to some extent, water resource management, increasing nitrogen use efficiency and using less inorganic fertilizers, support research to identify technology that doesn't work, and of course to be aware of what the weather and climate trends are. I think that's a big one, is that unless this information gets out and we really understand where we're likely heading, it doesn't do anyone good to help, in their planning. So one of the studies we're currently working on, and I just threw this in here because it's relevant to maybe solving some of the water quality problems, is that when we do modeling here in this watershed, we had the idea let's think about transforming agriculture on the landscape. And I mean shocking changes, like taking 50% of the row crops that are currently here, converting those to perennial grasses. And on the remaining row crops, let's reduce the amount of nutrients going on, meaning both inorganic fertilizers and manure, by 50% also. Do we get anywhere close to this 50% reduction goal that we're talking about? Those types of changes in this watershed are really non-starters for a lot of growers. Because it's risky. There's no income coming in of converting to a perennial grass. But what the research shows is that individually, either one of those scenarios gets us about halfway to our goal. If you do them together, by 2050, we can reach the 50% reduction goal. So I've been calling this the 50-50-50 by 2050 sort of approach. Can you transform half of the row crops to perennials? Can you reduce nutrients by a half on the remaining row crops that are being grown? And you can get a 50% reduction in that loading by 2050, about 40 years from now. It's possible, but how do you get there? It's a pretty big problem socially to think about getting to that point. Some other ideas, is that we've got to be proactive. Those that start planning and investing today are going to be ahead of the curve. And I think others will follow that path. I work in a department where there's a lot of breeding and genetics, plant breeding and genetics research going on. We continually need these new varieties. We can't assume that they're going to be a silver bullet, though, as though I keep hearing. I just don't think that that's true. We have to think about, how to better, manage our water resources and this crop for drop. If you're dealing anything with irrigation, does precision irrigation make sense? How to best use that type of precision ag in the future.
Question?
Yep.
Maybe I was misunderstanding you, but I thought according to your map, it was generally getting drier in the southwest, whereas for us it's getting wetter. Tell me more about why you're seeing the importance of that precision water use. If it is true that we're getting wetter.
You mean in our state, or?
Yep.
Yeah. I mainly throw that in there for if you're working on a sandier soil, let's say. I mean, this is sort of borrowed from a talk I gave in the Central Sands earlier in the year. So, there's some question whether or not, if you're dealing just with sands everywhere, does precision irrigation actually make a difference or not to yields for potato and vegetable crops? And we're still trying to figure that out right now. But a lot of the growers are investing. $50,000 for a field to invest in precision irrigation, you better make sure that you're getting a return on your investment if you do that. But yeah, other soils, I mean, irrigation and high cap wells are cropping up everywhere, whether it's getting wetter or not, but it's really the timing. I think the thing that I didn't show is that while, if annual precip sort of stays the same, maybe goes up a little bit, but the frequency of the heavy rainfall events is going up, that means that when it rains harder. But then that means that there's more time in between actual rainfall events. So that's when you have to start thinking about when you need to do your irrigation a little bit better. So thanks for asking that question. So some of you probably have heard about this big future of farming, big data, agroeco-informatics, sensor technologies, all these types of sensors and networks that we can have in our fields and on our farms that are basically piping all this data and information to us in real time. I think that really is the future.
What are they measuring?
Well,
Are they measuring the important variable? What can you measure right now in real time? Moisture?
Yep. Moisture.
Nitrogen? I don't know.
Yeah, well, that's where the technology is growing. And I think that the cost of some of those measurements is prohibitive right now for some people. Soil moisture, not so much. Weather stations are not that expensive to put in. But they're talking about these new biodegradable sensors that you actually are attached to plants that tell you something about the nitrogen or something about the health status of the crop.
Who's making biodegradable sensors?
There's lots of companies that are investing in that technology and researching it. I don't remember the names of them right now, but if you just searched on those terms, you turn up some ideas there. But this is in its infancy too. The other problem that's happening is that we're collecting so much data so quickly that we don't have anyone that really understands what to do with it in real time. And that's what I'm hearing from farmers. It's like, oh, I'm paying so-and-so or this company to provide this service, but I'm not seeing any increase in my yields. I feel like I'm getting ripped off probably. So, yeah, you have a question?
We as farmers understand what's going on with our soils, with the water retention, and the more and more we get our soils to the point where they're really the kind of life soils that we want, and we got good water retention. We also understand that with cover crops and stuff that we're sucking more carbon out, and we're keeping that land, from being open and stuff. We understand these things, and we see the yields, and we see our organic matter and stuff go up by doing these things. This is a proactive of the organic industry, really. That is the things that the organic industry has learned to do, and we're all learning to do that together. We have to be proactive on that, and we have to be the leaders, I think, for all ag, to be able to look at that. And whether it's in this area here, or it's down in my area in southwest Wisconsin, which has got some bad water samples coming out, I mean, for drinking water and stuff. Well, we have to be responsible
Yeah.
for that stuff.
Yeah. Great. Thank you for your viewpoint. So, yeah, why don't we just open up to questions? Go ahead. Yeah.
If you go back a slide or two where you talk about breeding programs. Okay, to double down on genetic research.
Yeah.
I would argue that we also need to discuss, should we not be focusing on breeding programs of winter annuals that are planted in the early fall? But then this also requires that we need to know more about what's going on with our changing climate, because you plant a winter annual in the fall, your late fall weather and your winter and early spring weather becomes big deals.
Yeah.
Warm, wet winters with a lot of ice is a disaster area. And like last April, that was colder and snowier all the time. Those are big deals.
Yeah.
But at the same time, we can't really achieve the goals, I don't think, without winter annuals.
Yeah. Good point. Yeah. Go ahead.
So what I really would like to have access to is some way to figure out, based on projections for the area where my farm is, for the 2040 to 2070 range, where can I go in the U.S. that currently has those conditions so I can figure out what they're doing?
Yeah, there's, I'd say about 10 years ago, there was,
Miles south or east?
yeah, that's called the analogs. And, in Wisconsin, people were saying, oh, we're going to be like Missouri or Arkansas by 2050. And I kind of shied away from sort of promoting that because I feel like the climate is changing in a way that climate there really isn't going to be exactly representative of what it's going to be like here where you're at, moving forward. It'll get you close, but maybe for planning purposes that's good enough, and it's probably an answer we need to figure out. Go ahead.
Don't these, these are all strategies, but isn't it, it's sort of a moving train, as I believe we increased our carbon emissions worldwide by about 2%, 2.8% or something last year.
Yep.
And as long as we increase that driver, I think it's unpredictable to say, okay, here's the problem, and here's how we become resilient to it, when the problem is it being exacerbated, and it's kind of an unknown of, okay, we're at 400 parts per million right now. Well, what happens when we reach 450 or some point beyond 400? Does the projections just suddenly fall in on themselves, and we get a rush toward some real problems?
Well, I think the climate projections, the models have that built into them. The different scenarios, RCP 6.0 versus 8.5, those, a couple of the lines were on some of those figures. Those are different scenarios of where atmospheric CO2 is.
Lowering.
Yeah. So optimistic or not so optimistic. So, we have this range. We kind of know we're going here, but it's kind of like a weather forecast 7 days out. Well, it's a snowfall forecast here going to be Monday. Well, one model says 2 inches, one says 8. That's kind of what we're talking about in the long term. So we know, we kind of have a good idea, good enough to be planning and thinking about what we should be doing. My concern on the discrepancy between our trends and hot days, because we haven't seen that increase yet compared to what the models are, at some point I worry we're going to have this massive step jump function where we go into a different regime, and it's going to challenge everyone. Everyone's going to be like, okay, now we're going to get 30, 90 degree days every summer. I'm not prepared for this. My dairy's not prepared for that. My livestock aren't going to be able to handle that. I needed 10 or 20 years of planning and investment to be there. So anyway, there were some other questions? Yeah, go ahead.
Well, I think that's an important point. There's a tipping point where we're focused on carbon now, but really the number one greenhouse gas is water vapor by far. And so with greenhouse gas such as carbon, will water vapor become the slippery slope, or the real lubricant on the slippery slope, and really cascade? Is that in the thinking at all, and climate modeling?
Well, it's in there. That one, yeah, that comes up periodically, and people like, is that really important? Is it not? There is a lot of focus on the CO2, the nitrous oxide, the methane. I think the other problem with the water vapor is that it impacts other things in the system. It impacts plant physiology. It impacts, the generation of rainfall patterns and that too. And so I'm not sure that's so much a slippery slope. Like I don't hear that discussion among the atmospheric scientists that I would talk to, but it's still there and something to be concerned about.
My thought is that you're gonna reach concentrations of water vapor that will cause it to really tip cascade effect, like you say, jumping to a different climate rather rapidly.
Yeah.
I have another question for you related to phosphorus. I understand a certain amount of phosphorus is water carried, water soluble. But really, isn't it mostly about soil movement? Because phosphorus pretty much affixes to soil, so if you could decrease soil movement, you could therefore decrease phosphorus loads under the plants. So what that, when you talk about perennialization of cropping and so forth, it's also, I think, a matter of redistribution of the dairy industry. In the sensitive watershed areas. That's a long-term thing.
Right,
Right, hopefully it's a long-term thing, because you can't make radical changes in the farm environment. But I think that's an important consideration. I guess I didn't give as much weight as 50% phosphorus movement is soluble with water alone.
And we didn't either before we started that project in this watershed. We were thinking 80-20 split, and it didn't end up that way. And then the light bulb goes on like, well, this is starting to make more sense now why we're having a hard time, because the Band-Aids that are being slapped on the landscape are only trapping half of the problem, unfortunately. But then you've got that climate change signal superimposed, and people would say, well, if we hadn't improved management practices, maybe the trend would have been going up because of the increase in extreme rainfall events. So maybe we're on this treadmill, we're kind of keeping up with that changing climate, but at some point we're going to lose the battle, and it may get worse before it gets better. So, are you going to break this off?
Yeah. So we can have a little bit of break before our 2:15 session begins, so I can get that loaded up. But I'm sure you can hang around.
I just put my contact information up there. If you want any of this presentation, all of it, give me an email. I can probably set up a box folder somewhere. You can give you a link and you can download it. Thank you for the questions. This was by far one of the most, the best presentation I've given on this, given the feedback and the questions you guys had.